Good morning. So, today we will continue the first topic on solar cell, and as we have discussed in the previous two lectures, primarily on various solar cell and the mechanism of how a solar cell, particularly a junction solar cell, works. So, before that I also discussed about the important points that when we consider a solar cell or photovoltaic cell, what are the things that we need to know, what are the fundamental things or basic things. So, first thing is anyway the absorption of light, or what we should say that the efficient absorption of light in a semiconductor material, and the second step is generation of charge carriers, and again the proper generation of charge carrier or efficiently the generation of charge carriers, and then the movement of charge carrier or transport of charge carriers to the outer circuit, which eventually gives the power. So, we also discussed about how one should consider a solar cell typical configuration and then see what are the equations or the characteristics that describe a solar cell. So, we have seen the dark characteristic of a solar cell, we have seen a solar cell when it is illuminated, and then we looked at what is the simplest equivalent circuit for a solar cell when it is illuminated. Then we found some important physical quantities which describe the solar cell in terms of say short circuit current or short circuit current density, open circuit voltage, field factor, efficiency, etc., and barrier height. Okay. And we also discussed about little bit about how one should control those parameters, and also what are the recombination and generation process. Then of course, we discussed detailed about how one can grow a solar cell material and then make different solar cell, and considering the amorphous silicon solar cell also, and then the plasmonic particle on solar cell. So, today in this lecture, this is a part of the first two lecture, I call it lecture 2A. In this lecture, we will continue with the discussion, but looking at some application or some problems or the basic things in little more the way to understand the subject in more fundamental point of view and address some questions on the first topic. So, let me just go to the first part of it, that is what we call the absorption of light in a material. So, the question comes, how photon absorption takes place in a semiconductor. We already have a discussion, but let us look at this question. If such question comes that how photon absorption takes place in a semiconductor, how do we understand this? The most important part is that when light falls on a semiconductor which is used for a solar cell, it is important to choose what is the energy of the light and what is the band gap of the semiconductor material that we are choosing. So, if we consider silicon, which has been discussed in the previous two lectures, its band gap is around 1.1 electron volt, and it is an indirect band gap semiconductor. But we gave enough reason why it is used in photovoltaics and why still the solar cell technology is basically based on the material silicon. Okay. So, if we consider other materials which we will discuss in the subsequent chapters like wide band gap semiconductors, then what is the absorption? So, that means when we change one semiconductor to another semiconductor, the absorption changes. When we change the material of a particular band gap to another material of another band gap, then the absorption changes. Okay. So, what we know broadly, when light interacts with a material, suppose semiconductor, there are three processes which happen are reflection of light, absorption of light and transmission of light. And when we talk about a solar cell, then what we would like to minimize is the reflection, and I already discussed with you about this anti-reflection coating which is used on solar cell. Second is we also would like to reduce the transmission, because if the light gets transmitted through the solar so the semiconductor, that means through the solar cell, then definitely these are not used. So, what we would like to do is more absorption of light in the solar cell. Okay. So, I already discussed with you, let us just make a very simple picture of absorption considering three classes of photon. One is a photon whose energy is less than the band gap energy of the semiconductor which is used for making a particular solar cell. So, what happens when the photon energy is less than the band gap energy? It will basically transmit through the semiconductor. Okay. So, if we consider the photons of solar spectrum whose energy range is less than the band gap of say silicon, okay. So, they will all transmitted through silicon or any other semiconductor, they will all transmitted through that semiconductor. Okay. The second category of light is the photon whose energy is more than the band gap energy. Okay. So, in this case what will happen, that when the photon strikes the semiconductor, then there will be an electron hole pair generation. So, you know how this electron hole pair generation takes place? Electron hole pair generation takes place if I have this conduction band and the valence band. This is energy of the photon and this is the band gap energy. Okay. So, electron hole pairs are generated when photon strikes and its energy is more than the band gap energy, and then electron and hole can be separated. That means, they can go to higher energy level, electron go to higher energy levels of the conduction band, okay. And then they can relax back to the band edges, giving some thermal energy. All right. So, this means the energy, if it is more than the energy of the photon, that will be absorbed, but there are quite a few thermalization laws because of the de-excitation of electron and emission of phonons. Okay. And third is when E photon is equal to band gap, and this is a perfect case where we know the absorption will take place, because the electron hole pair separation will take place. That means, electron will go from valence band to conduction band, it will rest at the edge. Okay. So, there is the thermalization loss is minimum. Absorption coefficient. What is absorption coefficient? And we continue with the discussion on absorption. So, if you look at the absorption coefficient, how do we define absorption coefficient? We define absorption of light okay. So, this is the incident intensity of light of photon and this is the intensity at a depth x okay, and alpha is the absorption coefficient. Alright, it is a very standard relation how the intensity of light decreases inside the material with depth okay, and that is been defined by a quantity called absorption coefficient. So, if we plot absorption coefficient whose the unit is the length inverse in centimeter inverse and plot with the absorption coefficient versus wavelength and look at for different semiconductors. Okay. So, there are various semiconductors which are given here, say gallium arsenide, germanium, silicon, indium phosphide, CDT, CDS, amorphous silicon. Okay. Some of them we will discuss in our next lectures, but let us look at silicon, the red one. We follow this curve, this is silicon and you can see how it is changing. Okay. So, if we come from this side of the axis, that means if we decrease the wavelength of light, then we will see that after certain wavelength there is an enhancement in the absorption coefficient and it becomes higher and higher at lower wavelength. That means at higher energy. What does it mean? It means that there is a band gap energy which actually gives the threshold which I discussed about EPH is equal to EG, and after that the light starts getting absorbed inside silicon okay, and it is higher and higher when we go to lower wavelength, and this is true for all materials. Suppose I consider another material say CDT, which we will discuss in the next lecture as a wide band gap semiconductor. So, look at CDT. CDT this it starts at much lower wavelength. So, that means its band gap is higher than silicon. Okay. Before the wavelengths which are more than this particular value, they are all getting transmitted. Okay. And as soon as we are approaching towards the lower wavelength side, they are getting absorbed, and then you can see there is an enhancement in the absorption coefficient for CDT, and this is true for all semiconductor material. Okay. So, therefore, it is extremely important that when we choose a material for say solar cell, we have to look at how its absorption coefficient varies. This is the first thing or first step of choosing a material for a photovoltaic cell or a solar cell. Okay. And then we also have to check the absorption coefficient or the magnitude of absorption coefficient, how good absorption coefficient is as per the particular plot which I have shown you here. So, theoretically one is to calculate or experimentally one is to verify and then choose the material and see at what particular energy regime or wavelength regime of the solar spectrum this particular material will be useful if it is used in a junction solar cell. Okay. Number 1 is band to band recombination. Number 2 is defect mediated recombination. This is also known as Shockley-Reed-Hall recombination, SRH recombination process. And third is Auger recombination. Okay, so what happened in all these three types of recombination? So when we shine light on a semiconductor or on a solar cell where the semiconductor is used, then electron can jump from valence band to conduction band and then it can fall back to the valence band. Okay. So therefore, it will recombine and it will be lost. Some photons will be generated and then it will not be useful for the generation of solar energy. So this is one process, band to band recombination. The second process is Shockley-Reed-Hall recombination process or defect mediated recombination. So if you remember when I was discussing about the synthesis of silicon, we have seen that there are many elements which are present as defect. Okay. It is not only the elements which are present as defect when we would like to make silicon to work as in a solar cell, we have to intentionally dope with trivalent and pentavalent element. Okay. And this is true for all junction solar cell, all materials used in the junction solar cell. And therefore, doping is a very important part in the solar cell technology. So, that means what we are intentionally doing or unintentionally doing is creating some defect level inside the band gap, some kind of defect levels inside the band gap. So, this is conduction band and this is valence band, and then we produce some kind of defect level. Okay. So, what it will do in the with the charge carrier? So, what can happen that when an electron is actually falling towards the valence band, it can be trapped inside that defect level for some time and then again it can fall. Okay. So, when this type of recombination takes place, we call a defect mediated recombination or Shockley-Reed-Hall recombination. And third is Auger recombination. Auger recombination actually takes place when we involve three different charge carriers or three charge carriers. Okay. How we involve three charge carriers? Three charge carrier means suppose we have an electron falling from conduction band to valence band and it gives rise to energetic photon. This photon can again take another electron from conduction band to higher energy level. Okay. So, when that electron falls back, the third electron or the third charge carrier, the second electron or the third charge carrier, then it will emit photon or phonon. Okay. So, whenever we shine light in a semiconductor which is used in a solar cell, first the absorption is taking place and then charge carrier generation and then this recombination which is competing with these two processes. Okay. So, therefore, one is to check or one is to when engineers the semiconductor or making a solar cell, one is to be very careful about how to reduce the recombination. Okay. So, that one can have a good number of charge carriers to be flown to the outer circuit and giving the power of a solar cell. Now, we ask the next question, okay? Define minority carrier lifetime. This is a very important issue for a solar cell. Minority carrier lifetime. So, what is minority carrier lifetime? So, what we have discussed in the solar cell, that when we suppose we dope any semiconductor material, okay, we make an n-type semiconductor or we make a p-type semiconductor. So, in n-type semiconductor, electrons are majority carriers, and in p-type semiconductor, holes are majority carriers. But there are minority carriers also. In n-type semiconductor, holes are minority carriers, and in p-type semiconductor, electrons are minority carriers. So, now when we shine light, what will happen? The number of majority carriers are huge, okay? And therefore, we are not going to change much the majority carriers. What we are going to change is a minority carrier, okay? Although the majority carriers are also being generated, because electron hole both are generated, but as the number of majority carriers, suppose electron in n-type semiconductor is huge, generation of few electrons will not make much difference in the number. But as the number of minority carriers in, say, holes in n-type semiconductors are very few, when we shine light, the holes which are being generated or created, that is the minority carriers, they will compete with the previous minority carriers which were there in the n-type semiconductor. Similarly, for p-type semiconductors. Okay. So, that means when we talk about a recombination process, the lifetime of these minority carriers are important, because now minority carriers are playing a role that how they are getting recombined. If they get recombined, okay, then definitely they are not useful for solar cell, the action. That is what we have seen, the 3 recombination process. So, its lifetime should be large. Okay. So, it should have a lifetime. Lifetime means after generation, before recombination, how long it can stay as a free charge particle or as a charge carrier which can contribute to the solar cell action. So, therefore, it is important to look at this minority carrier lifetime. And this minority carrier lifetime actually is decided by all these 3 recombination processes that I have discussed. That means band to band recombination, Shockley-Rittal recombination, and Auger recombination. All these 3 recombination processes actually contribute to decide what should be the minority carrier lifetime of a particular the semiconductor which is under study for a solar cell. And then the important part is that how they diffuse. Okay, the minority carriers, they have generated and they have to also diffuse through. So, one has to also calculate what is the diffusion length in a solar cell. Okay, so, diffusion length should be in such order that these charge carriers should diffuse and then they come out through to the outer circuit through the contacts which are used in a solar cell configuration. So, we also have to define a diffusion length which is diffusion length and this is diffusion coefficient. And this is anyway minority carrier lifetime. Okay. So, for a proper design of a solar cell, these 2 quantities, that minority carrier lifetime and diffusion length, are extremely important. Okay. Now, once we know all these basic quantities, that means absorption, generation, recombination, minority carrier lifetime and diffusion length. Now, we have to look at how we define a p-n junction and how one can see what is the active region where actually the solar cell works. Okay. So, now the question is, the heart of a junction solar cell is the semiconductor p-n junction that I have already discussed in my lectures. How do you calculate depletion width of a p-n junction? This is extremely important. So, what we have seen, what is depletion width? Let me again so, suppose this is a p type semiconductor, this is n type semiconductor, and p type semiconductor, you know, the holes are majority and there are some electrons. Okay. And n type semiconductor, electrons are majority and then there are some holes, okay, which are minority carrier, and as soon as we make a junction, this starts diffusion motion because of concentration gradient and eventually creating a depletion layer. Okay. So, we know that, and in this side this is negative and this side it is positive. Of say width d or w. These are the two notations which are used to define the depletion width or the width of the depletion region. Okay. So, now the question is how to get this idea of how much depletion width is. Suppose I have one n type silicon and an n type p type silicon and I make a p-n junction, then when the depletion layer is formed, what is the thickness typically of this depletion layer. So, one has to look at the mathematical calculation of that. But before that, if you look at this diagram, that you have this p side and n side, and then this is the Fermi level, this is valence band, this is conduction band, this is valence band, this is conduction band, okay, and this is actually what you have generated. This is called, you know, the depletion region is here with certain height, that is barrier height or barrier potential. Okay. So, we have to solve this particular problem. So, let us start from the simple Poisson equation, okay, because it is a problem of electrostatics. We have to calculate the, you know, the electric field and the potential, and from there we have to calculate the depth. Choose the Poisson equation which tells that how the gradient of electric field varies, and it is actually dependent on charge. So, suppose the depletion region is extended towards n side and it is also extended towards p side. So, this side it is minus x p and this side it is x n. So, what are the charges? Rho, for this condition it is q n a because they are acceptors, and for this condition it is q n d, that means they are donor. So, we know the charges, and then what we have to do, we have to solve this problem. Okay. Very simple mathematics. If we look at the electric field, just by solving this for this region, okay, this is the electric field, okay, with constant C1, and for this region the electric field is this and with the constant C2. So, now I put some condition. What is the condition? That the electric field at x is equal to minus x p is 0. So, I get the value of C1, okay, and the electric field at xn is again 0, because the electric field goes at xn where the depletion region is extended, and beyond that there is no electric field, and C2 we get the value of C2. So, this gives us this value of the xn and xp. Let me again give you this. So, that means this is p side, this is n side, that is how much, if this is 0, that how much it is extended to n side and p side. This is xp and xn. Okay. So, we get the value of xn and we get the value of xp, and you check that these values depend very critically on the potential height, which I have just now shown, that when you make a junction there is a potential height or potential barrier generated. It depends on the charge carrier concentration, acceptor concentration and donor concentration, similarly xp. So, what we are essentially calculating is the depletion with D or W is equal to xp plus xn, and when we do this we get this particular equation, and this is extremely important. So, whenever we start with a with a solar cell with a particular material, we have to look at it what is the depletion depth, because the photons are basically absorbed in that particular region, okay, which is the effective region of the solar cell, and then it depends on the potential height V naught, which is generated across the junction p n junction. It depends on the acceptor impurity concentration, it depends on donor impurity concentration, okay, and it also depends on the dielectric constant of the material which we are using. All right. So, this first important the mathematical quantity or the physical quantity which is derived mathematically and which is used for a solar cell designing. All right, you can go back to all the equations which I have discussed in the previous lecture, and what are the quantities at n, phi b, etc., and then open circuit voltage, short circuit current, field factor, efficiency, etc. You can again look back, and based on all this discussion, let me ask few question which are generally or frequently asked for a junction solar cell. So, first question: effective photovoltaic energy conversion, what are the most important steps? Okay. So, for effective photovoltaic energy generation, what is the first step? First step is the good absorption, generation of charge carrier, okay, efficient transport of the charge carriers by defeating as much as possible the recombination process, and then flow of the charge carriers in the outer circuit across any load which is used, so that you can generate power. Okay. Why the built-in electric field should be strong? So, his first question. The second question, why the built-in electric field should be strong? Okay. So, just now I have shown what is built-in potential and what is built-in electric field. So, what happens that in solar cell, this is actually the field, electric field, where the charge carriers get energy, because as soon as the charge carriers are generated, there is nothing which can push them to different directions. So, it is only possible by the built-in potential or built-in electric field which is generated across the junction because of formation of the junction. Okay. This is what we have discussed, and we have seen that typically the built-in potential of 1 volt is generated across the junction for a particular concentration of acceptor and donor. Okay. And they actually, if the built-in potential or built-in field is more, then the charge carrier separation will be efficient. Okay. How to make a desirable depletion region? So, I have already shown you the calculation of depletion region. So, what are the quantities that actually those control the depletion region width? The first thing which we have seen for a given semiconductor material, it is the potential height V naught, okay, that is built in potential, all right, and then the charge carrier densities, acceptor and donor charge carrier densities, they control what is the depletion width. So, if we decide a particular depletion width that you will design, you have to go back to the concentration values of the donor and acceptors, those are used in these semiconductors, and determine the depletion width. The fourth question, what are the advantages of heterojunction solar cell with respect to homojunction? This is a very interesting point. Actually, heterojunction we have not yet discussed. Heterojunction means when you have two different semiconductors. That means, for p type you use one particular semiconductor, for n type you use another semiconductor. In the next lecture, we are going to use or going to discuss about heterojunction solar cell, the CDT CDS solar cell, where CDT is used a particular semiconductor and CDS is used for another as another semiconductor. So, that means you make heterojunction, but is there any advantage over homojunction? Yes, there can be advantage, because the advantage is that when we choose or we make heterojunction, we can vary the band gap. Okay. So, one can be of band gap say 1.2 or 1.3 electron volt, another band gap is say 1.7 electron volt. So, we have seen just now that how absorption critically depends on band gap. So, therefore, if you have such combination of p and n junction, you can really tune the energy of solar spectrum which are getting absorbed inside the solar cell. Okay. So, this is the advantage of heterojunction solar cell, but there is a disadvantage also, that is what is mentioned. What are the disadvantages? The disadvantage is that when we grow material, suppose n type silicon and p type silicon, they are same material. Okay. If I n type silicon with another material is p type, that means they are dissimilar materials. So, one material fusing to another material which are not same can generate some kind of interface states or defects. Okay. And that what we have seen in the defect assisted or defect mediated the absorption process or recombination process. So, what happened that if we have defect in the material, then they use as a trap, and then it uses a recombination center. So, it is always better to make the material more defect free. So, these are disadvantages that you make for better absorption of charge carriers, you make an a heterojunction solar cell, but you give rise to certain defect. Now, why the front contact of a junction solar cell is grid type, that I have already discussed during our in the lecture, that generally it is make a gridded type. So, that you get maximum the illumination of light and also a good contact. Okay. Otherwise, it will be shadowed if you have a full contact of metallic layer. How to experimentally determine N? What information does it give about solar cell? So, N we have already calculated. You go back to the equation where we have calculated the value of N, that is ideality factor. Okay. So, ideality factor is basically it varies from say an ideality factor, ideal value is 1. Then we increase the ideality factor, that means it is having more R and G centers, that is recombination and generation center. So, one is to play with this ideality factor N and try to see what should be the value of ideality factor or optimum value of the ideality factor in order to use it efficiently for a solar cell. Now, we go to question 7, that maximizes of N maximizes VOC, however, it is not desirable. Why? So, if you look at the open circuit voltage equation which we have discussed in the previous lecture, the VOC is actually directly proportional to ideality factor n. But as I have mentioned that if you cannot keep on increasing n is basically you are creating more and more recombination centers. Okay? It will eventually decrease the current in the solar cell. Okay. We should have a condition where we have maximized or optimized VOC and optimized ISC, okay, so that we can get maximum efficiency. Therefore, the ideality factor value should be optimum for a solar cell. You can increase VOC value, but it will eventually reduce current. So, somewhere you have to play with this number and decide what should be the ideality factor. Now, next question, how to maximize ISC? ISC is short circuit current density. So, we know in order to increase the current density what we need is better illumination and absorption of light. So, we need intense illumination, we need good sunlight, okay. Otherwise we do not see a good current in the outside circuit. So, better illumination and more absorption of light, these are the two most important the physical process which give rise to higher current density ISC. And how to maximize efficiency, this is the final thing because this is a challenge to maximization of efficiency. So, we have already seen that there are certain processes which opposes the the solar cell to show its performance as per theoretical maxima of efficiency. Okay. But for a given solar cell, when we define the efficiency, we have to optimize the short circuit current density, we have to optimize the open circuit voltage, and we have to optimize fill factor. That means, these three quantities ISC, VOC and fill factor, these three are to be critically optimized in order to make the solar cell most efficient. Okay. And then of course, you have these two important thing RS and RSH. These are circuit parameters we have already discussed. RS is series resistance and RSH is the shunt resistance. So, in ideal case you should have a 0 series resistance and an infinite shunt resistance, okay, in order to optimize the fill factor and hence the efficiency of a solar cell. Okay. So, we have to look at all these questions when we try to understand and to make a solar cell with better performance and the design of a particular solar cell with higher efficiency. Thank you.